All right, so ready? So it's my pleasure to welcome Armando to the workshop. And Armando got his PhD from Berkeley in 2008, and now he's a professor at MIT. In his thesis at Berkeley, he developed this new approach to program thinking based on program sketching. And today he will tell us some applications and techniques to do with sketching. Go ahead.
There we go. Can you hear me? Perfect. All right, so today I'm going to tell you about this new way of looking at synthesis and this new approach to synthesis. The idea of synthesis goes back many years, but for a long time, the traditional view of synthesis, the 80s view of synthesis, if you will, was that synthesis meant starting from a complete formal specification, and then you would give that to your 1980s computer, and out would come provably correct code implementing exactly that specification. Unfortunately, there were many issues with this style of synthesis. Not only the fact that it's very, very difficult to come up with algorithms completely from scratch, but also from the fact that it's actually pretty hard to write complete formal specifications. There's a different way of looking at the synthesis problem, which we have been applying for several years now, which is rather than starting with a complete formal specification describing everything there is to describe about your algorithm, we start with a space of possible programs, a syntactically defined space of all the possible programs that you might consider for solving a particular task. So generally, the way you describe such a space of programs is as a parameterized program, where depending on the value that you pick for this parameter, you're going to get a different result. And now, once you have this space of programs, you can start applying constraints on the space of programs. And every constraint that you apply limits the space of programs. And these constraints might be of the form of input-output examples. So you have an input-output example that now limits the space to only those that satisfy those input-output examples. It might be maybe a test harness that you want this program to work correctly under. It might be some safety properties that you want the program to satisfy as it's executing. And the idea is that you can impose constraints on the space of programs, and eventually you will get a program that matches what you intended, that gets you what you want. And the advantage of this framework is that these constraints, these properties can come from many different places. It provides a very flexible approach for describing exactly what you want. And it also allows for, in some cases, a more interactive way of approaching the synthesis problem, where the user can come in and provide more and more properties, more and more requirements, and they can even convey insight about how they want the program to look like. So we have a language that we have been developing in my group for a while now, which is called Sketch. You can think of it as C with holes. You can actually leave missing pieces of code as part of this language, as well as assertions that you can use to define properties and constraints on these functions that you're creating. And so this is the language that you use to define these parameterized space of functions. And to give you a very simple example of the kind of things that you can describe in this language. So here we have, we want to write a function that takes the average between two numbers, but we want to do it in a way that we're not going to have overflow problems, that we're not going to get an integer that is too big. And so the way we're going to define this function is we're going to have an assertion that this value that we're returning, it should be equal to x plus y divided by 2, but we don't actually want to compute it as x plus y divided by 2. Instead, we're going to use what we call a generator, some way of describing a space of possible functions. And in this case, this generator takes a set of operands and a set of operators. That's how we're going to define the space of functions. So in this case, we say the set of operands that you're allowed to use are x over 2, y over 2, x mod 2, y mod 2, and 2. And the operators that you are allowed to use are addition and division. And so what we're defining here is a space of possible expressions, a very large space of possible expressions that now the system can solve and in a couple of seconds tell you that, well, here is one expression in that space that satisfies the property that you declared. So we have a mechanism for describing a space of functions together with a mechanism for describing properties and the ability to search very efficiently these very large spaces of functions. So, yes? So that's a very good question. So in this case, you're looking at x plus y just as actual integers. So now, and the basic, yes? That's a very good question. And this comes from the way we define the space of expressions that the program gets to choose from. And this is one of the things that you get with the style of synthesis, that you can impose restrictions, not just semantic restrictions about the behavior, but also structural constraints about how you expect the program that you're synthesizing to look like. And a lot of times, there are constraints that are actually easier to describe in terms of the structure, as opposed to semantically. This is particularly important when you're dealing with complexity, for example. If you're trying to synthesize a sorting algorithm, it can be tricky to describe to a system that you want an n log n algorithm as opposed to an n squared algorithm. But it's actually fairly easy to tell to the system, I want a divide and conquer solution, for example. So the basic technology that allows you to search these spaces of programs very efficiently is based on relatively tried and tested technology. We're taking a lot of ideas from the bounded model checking community in terms of taking these programs, unrolling loops, inlining functions, doing a lot of enumeration, and eventually getting systems of constraints that we can hand to a solver and have the solver find these unknowns for us. The thing that I want to focus on this talk is what can you do once you have such a mechanism? What can you do once you have a language that allows you to describe these spaces of programs and a mechanism to search these spaces very efficiently and to take these constraints that define your space of programs and to solve them very efficiently to get something that satisfies the constraints? Yes? Yeah, that's right. So this is simply saying, this is not guaranteeing at all that I shouldn't have overflows. And in fact, if you write something and you get an expression that is not the one you wanted, you could try and going and imposing more constraints. In fact, if you really, really wanted to write something that absolutely guarantees that you will never get an overflow, what you could do is actually write this as a repetition, where for every sub-expression, after every sub-expression, you're guaranteeing that this sub-expression will be less than some particular bound. In this particular case, the simple restriction that the system is searching for smaller expressions before searching for larger expressions, and the restriction that it can only use these operators and these operands is what gives you the restriction. That's right. Yeah, that's right. Okay. All right, so what can we do with a system like this? So the first thing that we can do is, given that we have a very expressive language here, the language actually supports heap allocated structures, it supports, it has some support for higher order functions. So let's say you want to do synthesis not for this very general language that is also very low level, but maybe you want to do synthesis for a high level language. Well, all you have to do is write a compiler, just a dumb compiler that compiles from your high level language to our language sketch. And for free, you now get a synthesizer for your high level language. And it turns out that if you can do that, you can actually do some really interesting things, because as part of this compilation process, you can introduce additional constraints, or you can introduce more flexibility into the compilation process. And so one of the interesting things that we have been able to do following this approach is actually an automated tutoring system for Python, for people learning Python programming, and being able to give them feedback about the exact errors they are making on their Python programs. The other thing you can do if you actually want to do more classical style synthesis, where you actually have pre and post conditions and you want to synthesize a provably correct function, yes? You need some way to map the results of these back to something that is meaningful in terms of the high-level language. Yes? Yes? The only reason to go back is if you want to do more than running it, if you're trying to tutor somebody, you want to give them some direct feedback in terms of the Python program that they wrote. Mm-hmm. So in the case of Python, and particularly the class of Python programs that we're targeting, where you're not interested in looking at a high order Python program and whether it works for all possible functions that you might pass it, but we're looking at the kind of introductory programming exercises where students might still use high-order functions, for example, but in a very limited way, and you're not trying to quantify over all possible functions. That's what would make it significantly harder and out of the scope of what we can do. And so, again, if you want to do more traditional synthesis, you have pre and post conditions, and you have some invariants. You can actually do that by essentially doing verification condition generation. And once you have your verification condition, you can actually express that verification condition, code it up in Sketch, and use that to not only infer parts of the program, but also infer parts of the pre and post condition, parts of the invariants. So you can actually get provably correct code out of this process. Interestingly, you can also use this to do program optimization, which might not be intuitive at first, that you need this machinery or that you can use it, but I'll show you in a few minutes how to do that. Also, for example, if you have a program with some properties that you want to make sure that these properties hold for all possible inputs, not just for the kind of bounded analysis that Sketch is able to do, again, what you can do is compile this program into a program that instead of manipulating concrete data, it's manipulating some representation of an abstract domain, which you can actually represent using data structures within the language. And then, once again, all of a sudden you have now a synthesizer that is reasoning in the abstract domain and that is able to give you provable guarantees about what you're manipulating. And interestingly, we have actually used this in a visual programming system that, if there's time at the end, I can show you. The main things that I want to focus on this talk are the automated tutoring system and this application to program optimization. The automated tutoring system was built primarily by my student Rishabh Singh. We've been collaborating with this with Sumit Guliani. Rishabh just graduated last year. He's now at MSR, and this was his thesis project. So the main idea behind the system is that you're trying to teach first-year students how to program. We're teaching them in Python, and you give them a programming exercise, and they come back with a solution that is almost right, but not quite there. And what you want is you want to give them the kind of feedback that a good instructor would give them. You want to tell them, yeah, this is almost correct, but here you shouldn't return derived. You should actually return this list containing 0. And this code is not really necessary. You can get rid of it. And here, range should not start at 0. It should start at 1. And if you make all those fixes, your program will work, right? And then you have some other student who thought up a completely different way of solving the same problem. So it's a completely different piece of code. It has a different looping structure. But you want to be able to also tell this student, oh yeah, this actually almost works if you change this 1 to a 0. If you change this greater than or equal to a greater than, then your code is correct. You're actually really, really close. This is the kind of feedback that you want to give, especially to the students who are just learning how to program, who are still developing those debugging skills that would allow them to figure this out from, say, an input-output example, right? So is this a synthesis problem? So it turns out it is. And because what you have here is you have a concrete goal that you want to get a program that is correct. And you can actually define a space of programs, namely all the different ways in which you can correct these programs. And you want to find a correct program out of that space. And you want to find a correct program that is as close as possible to the program that the student wrote, so that you're not going back to the student and just telling the student, oh, no, you're stupid. That's not how you do it. This is the right way to do it, despite the fact that the student might have been really, really close to a correct answer. So what we have here is we have a high-level language. In this case, it's Python. And so again, what we need is we want to start with just a compiler, going from Python to Sketch so that we can apply all these synthesis capabilities at the level of Python. And not only that, the students are not writing programs with holes. They're not describing space of programs. They're just writing a solution that they believe to be correct, even though it's not. And so what you have to do is you have to now, from that, infer the space of programs that the system is going to search. And that is done by providing an error model that describes the different kinds of corrections that you could do to a program, things like replacing a variable with another, replacing an operator with another, dealing with corner cases. And so the compiler, what it's going to do is weave that error model into the program itself so that you can get a sketch and you can rely on the synthesis machinery to do the search for you. So I'm going to start by talking about how do we compile Python to Sketch, and one of the most relevant things that you have to do there is deal with dynamic types. In principle, a lot of the programs that students are writing at this stage should not rely on dynamic typing. But in practice, if your system cannot reason about dynamic typing, it's not going to be able to catch a lot of the common errors that students are making in these kinds of programs. And the way we do this is actually not that different from the way you would do it if you were, say, writing a compiler from Python to C, for example, right? Essentially, what you have to do is you have to define some kind of type that can represent all the different types that you can have in Python. So we actually just have a structure. Again, this is just like you would have in C. And we have a flag that tells you what type it is. And we can say, well, if it's an integer, then the value is going to be in this integer value field. And if it's a Boolean, it's going to be in this Boolean value field. And if it's a string, it's going to be in the string field. And if it's a list, it's going to be in this field. And if it's a dictionary, it's going to be in this field. And if it's a tuple, it's going to be in this field. So now every single variable in your program is going to be of this type. And every single operation needs to actually check, OK, what is the real type? What does that flag tell me that your type really is? And you can define all your operators that way. So pictorially, we can represent it like that. We have a flag that tells us what type it is, and we have fields for all the different types. So for example, a list 1, 2 is actually an object that has the flag list, and it has a list with 2 values. And each one of these, in turn, is a pointer to another one of these objects that has the int flag, and that knows exactly what value of integer you're at. So again, this is no different from what you would do if you were writing a compiler from Python to C, except in this case, it's a compiler from Python to Sketch. And so what that means is that for all the operators, for example, for addition, if you're adding two integers, you get another integer. If you're adding two lists, you get another list. If you try to add a list to an integer, then you get an assertion failure. And these are the assertions that you can write in Sketch. And the goal of the synthesizer is to complete the program, to find that program in the space that will not have any of these assertions, in addition to the assertion that says that this should behave like the reference implementation. Question so far? Yes? That's right. So now, what about the error model? So the error model is expressed as a series of rewrite rules that tell you things like, oh, when you're returning something, maybe you should just return this list that has a 0. Or when you're looking at a range from A to B, maybe you should also consider the range from A plus 1 to B. Or if you have some kind of expression, maybe you should just replace it with false. And there are many, many rules like this that you can implement. Replacing a variable with another variable is a very, very common thing, especially in a language like Python, where because it's dynamically typed, the system will not tell you, oh, you haven't declared this variable, or this variable was of a different type. You should use this other variable. So what happens, for example, if you have an expression like this in your program and you have a rule that says range of something and something can turn into range of that something plus 1 and range of that something. So now after you apply that rule, what you have is that if you apply that rule to the first parameter, now that means that this first parameter could be 0, or it could be 1. But we would prefer for it to be 0, because that means that you're leaving the program alone. You're leaving things as the programmer wrote them in the beginning. You want to give the students corrections that are minimal, that make as few changes as possible in their code. And the way this transformation is encoded in Sketch is by essentially having an unknown that the synthesizer gets to discover that says, well, if you make this unknown true, then you're going to return this default choice. But if you make it false, then you're going to return this other option, and you're also going to keep track of the fact that you made this choice, so that later when you're trying to count how many changes you made and you're trying to minimize the number of changes, you can tell that when you applied this rule, you actually changed from the original expression to something different. You made a correction to your program. So what this gives us, again, is it takes us from a single Python program that the student wrote to the space of possible solutions described in Sketch, which the synthesizer can then search and find the solution. So in order to actually test this, we got a very large number of homework assignments from a MOOC version of this introductory programming course that is taught at MIT. It's 600. And we have some assignments from the classroom version of the course, some assignments from the MOOC version of the course. And these numbers are after filtering out trivially incorrect solutions trivially incorrect solutions where, for example, somebody just presses the button without actually writing any code. Or somebody just writes the name of a function but doesn't actually put anything inside it, or where somebody has a syntax error that doesn't even make it past the Python parser. So what we find here is, first of all, the average running time for giving these different corrections. We can see that for many of these assignments, we can actually compute the feedback in less than 5 seconds. Some of them take quite a bit more time. So these in particular is fairly slow because it's actually doing a lot of floating point computation. This one is doing a lot of string computation, which is much, much slower in our system. Now, in terms of the percentage of these submissions that we can produce feedback, so again, this is the percentage of incorrect submissions to which we could give a correction, excluding only the trivially incorrect solutions. Again, things with empty bodies or things that don't pass the parser. And so we can see that for some problems, we can actually get very, very high percentages. For some of the problems, the percentages are relatively low, not so much because of limitations on the search procedure, but more because of the kind of errors that students tend to make in some of these problems. Remember, this can only do local fixes. Yes? That's right. So, and in fact, for each of these, we have specialized rewrite rules for that particular problem. And in the paper, there are some interesting numbers showing, for example, how the percentages improve as you provide more specialized rewrite rules, and what happens if you apply rewrite rules designed for one problem to a different problem. So these are the numbers after you have specialized rewrite rules. And so the limitation here really is the kind of errors that students make. If a student is writing solutions that are completely off the mark, that are maybe giving the right answer to a wrong problem, they misunderstood the specification, maybe they misunderstand the semantics of the language in a way that you can't just have small local fixes, then you get low percentages like this one. For other problems, however, the kinds of common problems that students make really are these local errors where they misassign, they use the wrong variable, and this is what we're seeing. This is what we're seeing in this case. Yes? So these are fairly small. The largest program here is Hangman, and these are exercises where the students are writing on the order of 10, 12 lines of code. That said, when you get to the program that Sketch is analyzing, which has to take into account the implementations of all of these libraries and the implementations of all of these dynamic types, the sketches that the system is actually handling are on the order of about 1,000 lines of code. So many of these do require multiple coordinated changes. And in fact, at the end of this time, I'll show you a demo of the tool and the kind of changes and the kind of feedback that you can get. So, but the feedback is very much like what I showed in the first slide. Essentially, it's telling you, here are the 3 errors, and here you need to change it by this, here you need to change it by this, and here you need to change it by this. And in fact, one of the things that we have been working on more recently is how to make this feedback more pedagogically appropriate. Because if you're teaching introductory students, it's not always the best thing to do to immediately tell them, yes, this is how you fix it. Congratulations, you were almost done. You want to actually guide them through the process of discovering that this is the problem. But that's a lot easier to do if the system itself knows exactly what the problem is. It's a local change because it essentially amounts to turning the condition of that if then else into either unconditionally true or unconditionally false. Other questions? Yes. No, in this case, unless we can find a complete set of fixes that will make you equivalent to the original program, we provide no feedback. So, yes. So for many of these problems, there can be multiple solutions. And Sketch has the option of allowing you to use minimization criteria, but in general, it will only give you one solution. And if you run it again with a different random seed, you can get a different solution. Yep. Yes. That's a good question. There's actually, I think, a lot of opportunity in this space precisely because of the fact that you have very large amounts of data. One of the things, so if the way we actually went about creating these error models was we started with the obvious things, ran it through everything, and then find an incorrect submission that was not fixed. So you look at that incorrect solution and you say, okay, is this a local error? Yeah, it's a local error. It could be fixed in this rule. Let's introduce that rule and, again, run and see how many of the ones you didn't have are improved. And in the paper, you can see those graphs of how many iterations of this process it took to get to these numbers. But it was in the order of 5 or 6. Yes? So for some of these, the spaces of possible solutions are very, very large. They're on the order of 2 to the 200 possible programs that the system is analyzing symbolically and coming up with a solution. Yes? No, so what this is telling you is what this is telling you is essentially the upper bound of how many programs are fixable from this technique. How many programs are amenable to, what fraction of the programs are amenable to local fixes, and the scalability of the solver in terms of doing that style of fix. We're currently now in the process of actually essentially reapplying this with different iterations of the course, and actually looking at how the things from one course, from one semester, for example, generalize to solutions from other semesters and how things are affected in that way. One of our first usage models for this, when we used it for the first time, was actually not in the MOOC setting, but in a classroom setting, where essentially the TA receives 300 solutions. The TAs receive 300 solutions, and what you want to do is you want to go in, run the tool in batch mode through all 300 solutions, and in a couple of iterations get feedback for a very large number of these solutions that now makes it easy to go through the reminding cases and give personal feedback in that case. Yes? Well, and I think this comes back to this earlier question about the transplants, for example. Could you derive some of these rewrite rules by essentially looking at very close, syntactically close solutions where one of them was incorrect and the other one was correct, and being able to learn some of these rewrite rules from that? I think there's a lot of opportunities here from the fact that, again, we have very large amounts of data in order to refine this process to really minimize the effort that is required to use the technology. Yes? That's right. And one of the things, and this is why you don't want to just go and have one concrete rule for every error you have, and you want to keep your set of rules small. One of the things that you can do in order to improve the situation in that case is rank the rules based on how frequently they arise, so that you always run with a very small set of initial rules, and for anything that can be fixed with that, you're going to provide very quick feedback and have a hierarchy of rules based on that. Can a rewrite rule introduce what? No, the solver is just looking at unrolled versions of these programs, and it's actually checking that for all inputs within a given range, the loops terminate. So yes, we don't have an issue of introducing non-termination. That's right. Mm. Okay, so hopefully I've convinced you that you can actually use these synthesis infrastructure to automatically provide feedback. Now, the other application that I mentioned that I was going to highlight is how can you actually use the ability to synthesize invariants and the ability to do verified synthesis to optimize programs in the first place. So this work was actually started by my student Alvin Chung, who also just graduated and is starting as faculty member in Washington, the University of Washington. And this work is now being pushed forward by Shoaib Kamil, who is extending a lot of the original ideas to the domain of high-performance computing. So if you think about optimization, the traditional way that, say, compiler optimization works, and the way normally people think about compiler optimization is that some programmer went and wrote some naive source code, and then you're going to give this naive source code to an optimizing compiler, and as the name implies, you will get an optimal executable, or, well, in practice, a kind of OK executable. And this is how traditionally we think of compiler optimization. However, recently there has been a lot of very good work around generating code from domain-specific notations. And the idea is that if you have a domain-specific problem description, you can essentially throw a lot of computation power and a lot of domain knowledge into manipulating these domain-specific representation of your problem so that out you can get an implementation that really is close to optimal and that in many cases is much better and much faster than anything that can be written by hand because the system has much more horsepower to devote to this than a lowly programmer. And if you can get this domain knowledge into the system, you can actually get very, very good code out of these. The only problem with this approach, of course, is that it requires you to write your code in whatever this domain-specific notation is. And it only works if you write your code in that particular domain-specific notation. And that is great, but what do you do about existing source code? And in particular, if you have existing source code already in a big application that happens to be source code that belongs to this domain, it just wasn't written that way. And so the idea that we're exploring here is that can you take that source code and use synthesis to synthesize from that source code both a program in this domain-specific notation as well as the proof that this program in this domain-specific notation is equivalent to the source code that we had in the beginning. So the first incarnation of this idea that we tried was in this project that Alvin did in the context of actually data-intensive applications. So the way a lot of database applications are written these days is that you have this application code, and instead of interacting directly with the database, it's interacting with this object relational mapping framework, which essentially allows you to access the database without it looking like you're accessing a database. And this framework is then in charge of generating queries, going to the database, getting information back, which then this ORM library wraps into objects so that the application itself is always dealing with objects. It never has to switch paradigms and write SQL code, for example. And the only problem with that, this has great software engineering benefits, but it tends to lead to big performance problems. And part of the reason why it leads to performance problems is that a lot of times when people are using this framework, they end up with code like this. So what is this code doing? So this first call is essentially issuing a select query for all the users. And this one is essentially issuing a select query for all the roles. And then here we have two nested loops that are going and selecting users that match a particular role. And essentially what we're doing here is we're using nested loops to implement what we could have implemented in a query. And the difference is that when you implement things in a query, the database engine has 30 years of query optimization machinery inside it to give you a very, very efficient implementation of this. Whereas here, what we have are just two totally naive nested loops iterating over some Java data structures. So what we want to be able to do is automatically replace this to this so that we can leverage, again, these 30 years of query optimization machinery to make these fast. So what do we want to do? So what we have is we have this block of code that returns this array, this list of results. So what we have for this code is we have a post condition that says results equal some output expression involving the users and the roles. And if we could just figure out what this output expression is, and if we could just figure out these output expressions as an SQL expression, as an expression in this relational algebra, then we can just, and if we can prove that this is really a post condition for this block of code, then we can just replace this block of code with a query. But in order to do that, and in order to actually prove that this is the post condition for this block of code, we need to, from this post condition, generate some verification condition that inevitably is going to involve some loop invariants, which we also don't know, and we don't want to bother the user with providing them. But now what we have here is essentially a big constraint with 3 unknown functions, 3 unknown predicates. And we know what these predicates ought to look like. We don't know exactly what they are, but we know that they ought to be relational expressions of some form. And so now this is a synthesis problem that we can give to our synthesizer. So we can go from a program, which is the program that was out there in our code base, together with this unknown post condition and this unknown loop invariance, write a verification condition generator that, again, the verification condition generator does not have to know that there's going to be any synthesis involved. It's just very mechanically generating the verification condition from this unknown invariance and this unknown post condition. And now you have this synthesis problem that you need to solve. And if you can solve it, then you will know exactly the relational expression that this code is equal to. And you can just do the replacement and get your performance benefit. And when we do this in practice, we find that we can actually take a large existing code bases. In this case, this is an open source project management application, 62,000 lines of code. And there's actually a completely automated analysis that goes through, identifies potential candidates where you're issuing a query, and then you have some loops doing something to the results of that query, and then it tries to identify whether they are good candidates. And out of these candidates, it's able to, for a large fraction of them, infer the post conditions, infer the loop invariants, prove the equivalence to the imperative code, and then behind the programmer's back, do the substitution into a query. And what's really interesting is that once you do that substitution, you can get big performance improvements. For example, in a query that is doing selection, just by going from doing selection with just a loop with an if statement to pushing selection into the database, you can get a very high speed up. The speed up, of course, depends on how selective your predicate is, because you're not only saving from the fact that the database is doing the selection more efficiently, you're also saving from the fact that now you don't have to transfer as much data into your application. But what's really exciting is that for things like a join, where the user went and did a join by hand, what you can actually get is an asymptotic improvement in the performance of your code, because what you're doing is you're replacing an order n squared algorithm that the user had written in their Java code with an order n hash join, which the database is implementing internally because it has all the indexes, it knows how the data structures look like. So by lifting the level of abstraction from low-level imperative code to high-level SQL, we are enabling, again, 30 years of experience in performance optimization, in query optimization, to optimize our code. So Alvin has now been working with Shoaib on this question of how do we go from here to doing this for imperative codes for something like Fortran, where you might have a code like this that what you want to do is infer that actually it's an expression like this, where you're computing this value for all values of I and j in some domain. How much time do we have left? A minute or so. OK, we can wrap up in a minute. So essentially what we're looking for are invariants of this form that say for all ij in some domain, we have all these arrays equal to some expressions involving other arrays. And the synthesizer has to figure out the right expressions, the right array indexing, and generally your domain is partitioned into multiple things. So for example, even something as simple as a loop like this, you will have multiple different regions that the invariant has to refer to. So this is actually quite a bit of a challenge, first of all, because the invariants can be very, very big, the invariants that you're trying to infer. They involve complex floating point arithmetic. And most importantly, they have this universal quantification. And I'm just going to tell you in 30 seconds what the story with this universal quantification is. So for synthesis, essentially, we're solving a problem that says, for all C, there exists a value for these parameters that works for all inputs. And in this case, our program looks something like this. We're saying, yeah, if the outer invariant is true, then assert something like this. The problem is, if this outer invariant has a universal quantifier, that means that now you have an exist for all exist problem, which is quite a bit harder than just an exist for all problem. The key here is to notice that it's always safe to weaken this condition. So if you make it more true, it's OK. And you'll never get a wrong answer from doing that. And so what we can do is, instead of saying for all ij in the entire domain, we can say for ij in some particular small set E. Now, if we pick the set E incorrectly, then we'll just get an unsatisfiable solution. But the key is that we can actually let the synthesizer pick the set E. Because as long as it finds a set E that makes it work, then we're good. Then everything works. So right now, we're at the stage where we just ran our first benchmark through this system. It's called Cloverleaf. It's a benchmark from DOE that has several dozen stencil kernels. And the most complex one takes 20 hours to solve on 15 cores, which might seem like a long time to compile a program. But if you think about this not as a compilation process, but as a way of taking this legacy application and upgrading to work on a DSL so that from then on, it's future-proof and it can be targeted to different architectures, 20 hours on 15 cores is actually not that long. So to conclude, there's more to synthesis than what you normally think of as synthesis. And you can do this too. All our infrastructure is open source. And you can just download it from our website.
Questions? Yeah.
Yes.
Probably I missed the point, but you talked about proof of equivalence when replacing Java code with SQL code, for example. And you didn't show how this proof of equivalence is given by your tool. So do I just have to compare and then decide myself whether it does the same thing?
No. The system is actually generating all the invariants necessary to prove the equivalence. So what you get once the synthesis process finishes is you get this verification condition with all the necessary invariants filled in. And now you can just give it to a theorem prover like Z3, which in less than a second it tells you, yes, this works. And it's able to do it very, very efficiently because of the fact that the synthesizer has already done all the work of finding all the inductive invariants that are necessary to prove equivalence. Yes?
How modular is it? Because I guess that if you now were to synthesize some kind of code, like swap some logic in the program, it's a non-local change. It might affect something somewhere else that may, let's say, not break functionally, but make something less efficient.
So overall, the replacements that were made, they're provably correct, and they're proved to be completely semantics preserving. So in terms of introducing bugs, that's not an issue. If you in some cases, assembling these blocks of code requires inlining doing a lot of inlining before you get to the point where you have a big chunk with nested loops that you can then work on. And what that means is that the optimization will work in that particular, will be applied in that particular context. But when other contexts call some subset of these functionality, they're just calling the original functions.
Okay, I think that's it. So we can run over time. You can take the discussion in the break. So we're going to have like a 15-minute break.